All right. So as I announced in the announcement, we're going to talk today about how to interpret deep learning systems. And normally I would start my talks with some kind of a warm-up exercise, which is a bit difficult now because we are, well, connected virtually, but we can still give it a try. So what I'm going to do is I'm going to show you some pictures, and you have to indicate whether the thing in the picture is real or fake. And so the way we're going to do this is you will have to show yourself. And then if you think that the picture is real, you do a thumbs up. And if you think it is fake, you do a thumbs down. And then Andrea will indicate whether the majority thinks it is a real or a fake picture.
Okay. Don't you want that we use the chat? No, you prefer that we use video?
Let's do video. Let's do video so we can see all your faces. At least you guys can see each other's faces because I cannot see anything. All right, so open up your webcams and get ready for the first picture, which is this one. Is it real or fake? All right, Andrea, you'll have to tell me what people are thinking because I cannot see them.
Well, me neither, actually.
Okay, because there's nobody who turned on their webcams.
I did.
Okay, so Andrea, you cannot see the people?
No, I can't see.
I see them. They're all thumbs down.
Okay. So Pablo is our referee here. So thumbs down. Okay, this one is fake. All right. How about this one?
Some thumbs up. Yeah, only thumbs up, and some undecided people.
Okay. This one? Three, two.
A few thumbs up. Yeah, thumbs are coming up. Oh, one skeptical.
Okay. This one? Any thumbs up for this one?
No.
No. All right. And then the last one. Thumbs up or thumbs down?
It's beautiful.
One down,
like
two, a
it,
few
so
down.
I say up.
One, there's one up. But most
All right.
down.
So I hope that the next one works because the next one is a video. So let me just see if I can.
Okay.
Can I click this? Let me just turn off the pointer. All right, it's loading.
It's coming.
I hope so.
Okay.
That's true. I know that.
Well, that's more sport than what I do.
Yeah. Oh, wait.
Okay, so what is this going to be? Thumbs up or thumbs down?
It was up and then it went down.
Can you play it again? Play it again.
Down, I see. Thumbs down.
It was up it's up at the beginning and then it's down for me.
Yeah, half true, half fake.
Yeah, 50-50 then for this one. So this one's actually from a commercial for a telephone or internet provider in India. So I'm sad to say that this one is fake, unfortunately. It would be very cool if turtles could really sprint like that. Okay, can I go to the next slide, please? No, stop. Okay, so enough for the warm-up. So clearly there were some pictures that were clearly fake and some were clearly real. Just about this house, which I think was the trickiest one. This is actually a real house, and there's actually a whole set of them in this sort of neighborhood. The thing that gave it away, I think, could be the curtains that are still hanging top down. But in each of these cases, you can probably think of a reason why this image is fake. Like with this boat, you can argue, well, boats are not very aerodynamic, so they don't fly very well. So this is probably fake. And many of these decisions that you're making are motivated by well, laws of physics or some previous experience. There's nothing that prevents a house from being upside down, but you know that most houses are right side up. So you can argue, well, this is not what a house is supposed to look like, and therefore it's probably fake, even though this is a real picture. So the explanation that you have for a given decision is tied to some understanding of a mechanism, how things work in the world. Now, with deep learning algorithms are not bound by any physics or any mechanisms in which the world works. And actually, decisions that are made by deep learning systems are just based on a sequence of mathematical operations. They're just matrix multiplications and vector additions. Now, actually, these mathematical operations are very precisely defined. We know exactly what is going on inside. We know the values of that go into these matrices. We know the inputs. We know all the intermediate values. And so in a way, we can explain our deep learning decisions with 100% precision. We know exactly what is going on. Still, people like to think of deep learning models as black boxes rather than glass boxes. And that is mostly because these deep learning decisions are not really tied to any mechanism that we are familiar with. Just to give you a very practical example. So here's the wave equation. And in this model, like most physical models, we only have very few parameters. And so each of these parameters can have some physical meaning. So for instance, if C is low or if C is high, then we know exactly what it means and what kind of effect it has on the model outcomes. So let's say that we can fit a wave propagation scenario with a 1 million parameter deep learning model. Then you could wonder, well, what is the meaning of the, say, 20,000 parameter? How much does it contribute to the output? And actually, if you look at most of the parameters in the deep learning model don't actually contribute at any given moment to the prediction. So looking at these parameters doesn't necessarily give you a physical explanation, and that is hard for us to comprehend. Now, we really want to actually understand these deep learning decisions because we want to make sure that these decisions are correct. In some cases, it doesn't really matter, right? For handwritten digit recognition, it doesn't matter so much. But there are applications like for self-driving cars, for missile defense systems, power plant monitoring, and earthquake early warning, that we want to be sure that the decisions that are made are 100% correct. Also, a bit outside of our domain, we want to also be sure that the decisions are ethical for instance, insurance policies or mortgage assignment if you want to buy a house, for very practical things like law enforcement and crime prediction. And lastly, we also want to make sure that our deep learning decisions are consistent. If we are processing large volumes of data, and at first it seems that the results are correct, for instance, for earthquake detection in DAS data, then we want to be sure that it remains to be correct when we keep doing this for, let's say, 1 year of data. And just to give you some examples of when things are going wrong, here's a picture from a digital camera where you're taking a picture of a group of Asian people, and then the AI believes that that people are blinking, which you could say is either funny or deeply racist, depending on your point of view on this. But perhaps a more serious matter is when AI is used in law enforcement. So Amazon is selling this facial recognition software, but some scientists have found that, especially on darker females, the performance of this model is actually pretty bad. So what it means in practice is that, well, if you are a woman of color, then there is a 1 out of 3 chance that you are being misclassified by this software. And we can actually weaponize this, right? Because I've talked before about the adversarial attacks and adversarial examples, and how we can actively try to fool the deep learning model and tricking it into thinking that you're somebody else. Imagine that you are a wanted criminal or terrorist going to the airport, and if you were to wear these funny glasses, then you will be classified as a different person, and so you can basically pass all these hidden security checks. So this is why we really want to understand how a deep learning model comes to a decision, so that we can evaluate whether or not the decision is correct just based on the interpretation. Now, one reason why deep learning systems are often wrong is due to something called clever Hans behavior. So clever Hans was not this guy, but it was a horse, this horse in the background. And as the name suggests, he was very clever because he could do all sorts of calculations and arithmetics. So this is the handler, Wilhelm von Osten, and he could give some kind of a hard sum like addition, subtraction, multiplication, and so on. And then let's say, for instance, you would give the sum, what is 3 plus 5? And then the horse would tap his hoof on the ground 8 times, and to indicate that 3 plus 5 equals 8. And he was right most of the time, actually. So even for very large summations, he was doing pretty well on that. But then there was this psychologist, Oskar Pfungst, and he found out that actually the horse is not doing the computations in its head. No, instead it's just tapping his hoof until the handler, so this guy, would respond in a certain way, just with this body language, like tensing up a little bit, indicating that the horse is almost there. And then, well, when the horse actually got to the right number, the person relaxed, and the horse would then interpret that as, okay, now I can stop tapping my hoof. So even though the horse got the right answer most of the time, it is not because it was actually a clever horse and making this computation, but because it was only looking at different cues that come from the handler or from the audience. So being right for the wrong reason is a very common thing in deep learning systems. And this is something that we really don't want. Just to give you a practical example. So let's say that we have a deep learning model that we use to evaluate the weather in Paris. So whether something is, whether it is sunny or rainy, based on pictures taken with a phone. So what we do for training is we download a lot of pictures from Google and then train our model on whether, deciding whether it is rainy or sunny in that picture. And on that, the model performance is very good. But when the model is used in the real world, then the performance gets worse. Now, why does this happen? Okay, so looking at our training data, we see pictures like these, right? Where it's clearly either very nicely sunny, like over here, or just rainy, and pictures like these. But now in the real world, if we look at what pictures we could get, then, well, very likely we are to see pictures like these. Now, is there anyone in the audience who could guess why the performance on these pictures would be so much worse than the performance on those pictures? Is there anyone in the audience who wants to make a guess?
No umbrella first.
Yes, no umbrella.
Yes, exactly. Right. If we look in these pictures, we see either people in flip-flops and shorts and sunglasses, or here we see people with umbrellas and coats. And whereas if we look at these pictures, well, in these two pictures, there's nobody. And over here, well, there are two people, but they're not exactly dressed for the weather. So it is easy to think that, well, maybe this deep learning model is actually not looking at the clouds or the streets, but just looking at people and then deciding based on the people whether it is sunny or rainy. Now, there's actually a way that we can figure out what a deep learning model is looking for. And this is what is called saliency maps. So it's very hard to interpret individual parameters in a deep learning model, but we can still interpret the inputs in some way. So what a saliency map is it indicates in the input which parts of the input contributes most to a given prediction. So let's say that this is our input. We have this picture here. And then we set the prediction to cat. And then we ask, okay, given that the prediction is a cat, what would be the part of the input that contributes most to this prediction? Or if we were to set our prediction to dog, then, okay, which part of the input would then contribute to the prediction of it being a dog? Right, so here we can clearly see that, well, if we ask for a cat, then it is pointing at the cat, and if we ask for a dog, it is pointing at the dog, which is exactly what we want. Now, in some situations, it actually uses other information that we don't really want it to use. So here is a very good example from this, this very nice Nature paper, where this group of researchers had a set of leaves. This is from a particular bead, and the machine learning model had to evaluate whether this plant was healthy or if the plant was sick. Right. So on the right, we see some examples where the plant was sick, and clearly there are these dark spots. So given a picture of a leaf, the deep learning model had to evaluate whether the plant was healthy or sick. Now, in the first two examples, if we apply this saliency mapping, then we can see that the biggest part of the input that contributes most to the prediction is actually on the leaf, right? Which means that the deep learning model is looking at the leaf and then based on that makes a decision. But then there are other cases, for instance, this picture here on the right, where we can clearly see that the leaf has these spots. But if we then visualize what the deep learning model was looking for, and actually it is looking something like to the top left of this leaf. So it would be looking somewhere over here. And there was nothing there that really could inform a decision. But for some reason, it was looking over here and it still arrived at the right answer, which means that maybe there's something in the way that the picture is taken, for instance, in terms of the lighting or the position of the leaf, that the deep learning model memorized and therefore could use as a shortcut in making a prediction that is correct, but it is correct for the wrong reason. And so if we identify this, then we can immediately discard the decision that was made because it was made based on the wrong kind of information. Now, there is a drawback with these saliency maps, namely that it tells you which part of the input is important, but it doesn't tell you why. So here's an example of a dog. This is a Siberian Husky. And so if we ask, so let's say that we set the prediction to a Siberian Husky, then this would be the part of the input that is used in informing that particular decision. But this is the input that is being used if the prediction were it to be a transverse flute, right? That's the flute that you play like this. And it's actually the same region of the image that is being used for this prediction. So even though we know what the model is looking at, we don't really know what it does with that kind of information. So in this particular case, we have this little dog, it's a poodle, and the model was looking at the right part of the picture for the classification, but the classification itself was that this is a cat. So the prediction is that it is a cat. It was looking at this part of the image, and still the prediction is wrong, and we don't know why. Okay, so Another way we can look or try to interpret our models is through activation maximization methods. So one of the most commonly used architectures used in deep learning is this convolutional neural network, which basically scans the input to create some intermediate output. Then again, scans the intermediate output to produce the next output, and keeps scanning subsequent reworkings of the input to produce more and more and more abstract representations of the input, based on which you can then finally make a decision. For instance, that there is a car in this image and not a bicycle. So we can now wonder, okay, what does each layer in this model actually see? The way we do this is we just take an image with random noise. And then what we do is we select one layer. And then we change the noise a little bit. We push the noise in a particular direction such that the output of the first layer gets higher. Right? And if we keep doing that, if we keep modifying the image with random noise a little bit, so that the output of this layer gets bigger and bigger, then eventually we will converge to a particular pattern in this input image, which maximizes the output of this particular layer. And then we can do it again for the next layer. So we keep modifying this picture until we get a pattern that maximizes the activation of the second layer. And we keep doing that for all the layers, and then we see what happens. Now, as it turns out, the first couple of layers usually only see very basic structures and motifs. Like for instance, here we just have lines and contrasts and different orientations. Then if we visualize some intermediate layers, then these basic motifs are being combined into more complicated structures. Like here we see eyes and noses and mouths appearing, so this kind of structures in the input would then maximize the output of these intermediate layers. And then finally, if we look at the last layers in a model, then we really start to see some complicated images appearing, in this case of faces or of cars or whatever you are looking at. So let's say that we have a neural network that is used to identify or recognize a dumbbell. A dumbbell is a weight that you use in the gym. So many of these pictures look like these. And then if we then visualize in a slightly different way what the network is looking for, then we tend to see things like these. Now, what is clear in all these images is that, well, we clearly see the weights that are on this dumbbell, but in many cases, we also see something that looks like an arm, right? Over here, and especially over here, we kind of see that many of these dumbbells have an arm attached to it. So as far as the model is concerned, a dumbbell is only a dumbbell when there is an arm attached to it. So in that case, this would not be a dumbbell. And so if it were to make a prediction on this image, whether it is a dumbbell or not, then it is quite likely that it says no, even though it is wrong. But we can try to sort of understand that by looking at these activation maximizations. So in this case, it is clear that you need to train your model with more pictures like these that do not have an arm in it, to make sure that the arm is not important in making the decision. Okay, so unfortunately for us, this is not very helpful because most of our data look like this. So you can imagine that the first layers will have some wiggles, and then the intermediate layers will have some more wiggles, and then the last layers will also have wiggles, right? So yes, of course, we know that there will be wiggles in the input, but that doesn't really help us to understand what exactly it is looking for and how it is using that kind of information in making a prediction. So it would be very hard for us to use this to guide the training process. Okay, so just an intermediate recap. As I said, deep learning systems are hard to interpret because they have so many parameters and they're not constrained by any mechanism. And understanding the origin of deep predictions is quite important to ensure accurate, ethical, and consistent performance in real-world applications. So think of self-driving cars and criminal profiling. And there are some techniques that exist to visualize which parts of the inputs or which structures in the inputs are important for making these decisions, but don't really tell you why they are important and what you can then do to further interpret the prediction. Now, in spite of that I just said that it is very important to interpret deep learning predictions, I'm going to argue that actually it is not that important to interpret deep learning decisions. And this is for actually quite a technical reason why I think that this is the case. Okay, so maybe as you know, many of these very big deep learning models from Google and Facebook, they are very, very deep and they have many millions of parameters, even though sometimes the training set does not contain millions and millions of training samples. So in a way, these very deep neural networks are severely under-constrained functions. To give you an example, the state-of-the-art language model, BERT, contains over 300 million parameters. And it is true that it has been trained on also millions and millions of words, but they don't necessarily form millions and millions of samples. So also BERT is an under-constrained function. But you can then ask, okay, what actually happens when our models become more and more complex given a certain amount of data? Okay, so here's an example where or actually these guys, they generated a simple data set from a very basic parabola. So it has 3 parameters, the underlying model, and then there's some noise because our measurements always contain noise. And so the ideal fit would just be a parabola, right, which is the generating model for this data set. Now, many of our physical models are actually much simpler than the underlying generating model because we do not include, for instance, fault roughness and all sorts of temperature effects and pressure and gravity and God knows what. So usually our models are, our physical models are an underfit to the data. They are a simpler version of reality. And so the accuracy of those models is not always great if you deviate far from some assumptions that you're making. Now, if you're going to fit a model with lots and lots of parameters, then what tends to happen is that you fit your data quite well, but then in between, there are these large excursions due to the very high order of, in this case, a polynomial that you're fitting. So if you were to evaluate this model on new data, let's say that we were to make a new measurement somewhere around here, then the prediction for this overfit model would be that that value would be over there, which is clearly very wrong. And so what we often see in deep learning is that if we go to very big models, then the performance on the training set is very good, right? So the training set are these black dots. Performance on the training set is very good. Then performance on the validation or test set, which would fall in between these training points, would usually be very poor. But what happens if we now going to fit a 1 million parameter model to this data set? Then we'd get something like this. So curiously, if you have this, a massively under-constrained function, then it tends to just perform some kind of linear interpretation between these data points. And this is what could be the reason for a phenomenon that's called a deep double descent, which has been first reported about a year ago. So what tends to happen if you increase the size of the model is that at first, when your model is underfit, then it doesn't perform very well, but then you make it more complex and more expressive. And then the error on the test set goes down. But then if you make it bigger and bigger and more complex again, then it starts to overfit, and then the performance on your test set tends to go up again. And the conventional wisdom was that if you just keep doing this, then the performance on the test set will get worse and worse and worse because you're just overfitting more and more. But what tends to happen in reality is that actually after some maximum, the performance on the test set gets better and better and better again. And actually it gets much better than this sort of optimum that we found before. So just to bring this back with these 4 panels, A, B, C, D over here, A would be our underfit model. So we have too few parameters to fit the data. B would be something like an ideal fit, where we have as little parameters as possible, but no fewer. Then this point, this maximum, would be a situation where we are starting to overfit our model. But then if we keep adding more and more parameters, then we're actually getting this direct fit, this linear interpolation between data points. So what I would argue is that extreme overfitting is actually a good thing, because it tends to this interpolation between data points. And so what it means is if we're adding new data within this regime, within this range of data points, let's say that we're to add a new data point over there, then because it's just simply interpolating, the prediction that we have will not be very wrong, right? So there is some scattering of data here, but if we are going to evaluate our model on new data, then the uncertainty or the error in the prediction would be of the order of the standard deviation of the data. So that is acceptable, right? We cannot do any better. However, if we have new data that falls outside of this training range, like for instance over here, then, well, deep learning models are very, very bad at extrapolating. As it turns out, recently has been found if you use ReLU activations, then your models just become linear models outside of this range of the training data. So it is very likely that any data that falls outside of your training data support the predictions for those data will be wrong. So as long as our data are within the training distribution, we actually don't need to interpret our decision, right? Because as long as they are within the distribution, we know that the predictions are very well constrained by the training set, and it's simply interpolating, so it cannot make very big outliers, and it cannot make very big mistakes within our training range. However, when the data falls outside of our training distribution, then it is very likely that the predictions are wrong. So instead of trying to interpret a deep learning decision and trying to figure out why certain predictions are made in order to evaluate their accuracy, we can simply now turn this into an outlier detection problem, where we have to decide whether our new data falls within the training distribution or whether it falls outside of the training distribution. If it is within the training distribution, then we're fine, then we can trust the prediction. If it falls outside of the distribution, then we know that we cannot trust it. And then we can ask for instance, a human intervention. And this is a much, much simpler problem, right? This is much easier to do than actually interpreting all those parameters. Now, it is of course not as simple as just looking at your input and then trying to interpolate between that. So here is a funny example where we have this little black box that has been trained to recognize either cats or dogs. So if you give it a cat, then it says, well, this is a cat, yay. And well, here's a dog. That's also easy, right? This is an easy prediction. But then you give it a kangaroo. Well, I mean, it can only tell you whether it is a cat or a dog. So it just guessed that this is some form of a dog. But the crazier it gets, you still get the same predictions that either things are cats or dogs. And unfortunately, we cannot identify this as an outlier by just interpolating between cats and dogs. This is an image, and interpolating between individual pixels doesn't really help you in determining whether this is an outlier or not. So this interpolation that I showed before actually happens in some kind of a higher dimensional abstract space, which we cannot directly access just by looking at the input. So here is a recent real-world example of why this is so difficult. These pictures on the left here, these are from a famous data set called Cypher10. So ImageNet and Cypher10 are data sets that are used in many computer vision and deep learning tasks. So usually when people propose a new method, they test that method on either Cypher10 or ImageNet. And so what these people from Berkeley did is they created a new data set that looked very similar in terms of content, right? It has birds and airplanes and dogs and so on, and they're all similar quality. And this is a horse and that is a horse, right? So you cannot really tell that there is much of a difference between these images, other than just a slightly different setting. But as it turns out, if you train a model on the original Cypher10 or ImageNet dataset and then evaluate it on this new dataset, then the accuracy drops by as much as 15%, which for this benchmark is huge, because normally people try to squeeze another like 0.1% out of their models with new methods. So if you drop the performance by 15%, that is absolutely massive for these data sets. And clearly we cannot really tell that these images are much harder to solve than images over here, right? And so we cannot really say that these are outliers, that these do not fall within the training distribution just by looking at the input. But fortunately, there are actually lots of out of distribution or anomaly detection techniques that's already put in place for many years. So for instance, what we could do is we could look at some of the principal components of the intermediate layer outputs. We can perform clustering of the latent space. One technique that I like a lot is using an autoencoder. So let's say that you have a cat detector, which predicts whether something is a cat or a dog. Then what you can do is you can couple that model with an autoencoder, which simply tries to reconstruct the original input. So you have a picture of a cat that goes into your model, and then the output will be a reconstruction of that input. Now, if your input falls within the training set, then the output of the autoencoder, the reconstruction, will probably be quite good or acceptable. Whereas if your sample falls outside of the training distribution, then the autoencoder doesn't know what to do with it, and then the reconstruction error will be very large. So this is a very simple way of just having some kind of a first order check whether the input is known. So whether the input falls within the training distribution or if it falls outside of it. But we can also do general adversarial training on the input to decide whether the input is something familiar or not. We can do something like contrastive learning or other forms of representation learning. And we can do something that's called Bayesian dropout, where you are evaluating the precision of the prediction. So not the accuracy, but you evaluate the precision or the uncertainty in the precision in the prediction. And then for data samples that fall within the training set, that precision will be acceptable, or the uncertainty will be small. But as you go farther away from the training set, the uncertainty starts to increase, which is something that the Bayesian dropout can most likely tell you. Okay, so with that, I think I should just wrap up. So as I said before, deep learning model predictions are not tied to any physical or empirical mechanism, so they're quite difficult to interpret or verify. And this is quite problematic for some real-world applications because we want our results to be accurate, consistent, and ethical. So we do not really know whether a prediction falls into these three categories or not by just looking at the output value. And so we do not really know whether we can trust the results or whether we should ask for instance, human intervention to verify a result. And many conventional interpretation techniques don't really tell you why a given prediction was made. And so they're often not as useful as they're being advertised. Now, some recent work has shown that very large deep learning models actually simply interpolate between training samples. And this gives them very good performance also on new data, as long as the new data falls within the support of the training distribution. So in order for us to figure out whether we can trust deep learning predictions, we have to figure out whether our data falls within the support of the training distribution or falls outside of that. Okay, and then finally, while I'm taking questions, I will leave you with one of the hardest problems that wherever conceived in deep learning, which is telling the difference between a muffin and a chihuahua. Okay, so with this, I will just open the floor for questions and comments. Thank you.